Let me take a numerical example and explain you how this translation is happening from logical address to physical address. So remember, logical address is the address generated by CPU. It thinks that the program is generated or the program is loaded, the process is loaded from address number 0. So watch this one. So I'll take a small example. Let us assume that the memory is containing 64 bytes. That's it. Not real, but then let's keep it simple, 64 bytes. So if you have 64 bytes, then how many bits are required to address this 64 bytes? It is 2 power 6. 2 power 6 is 64, right? Therefore 6 bits will be present in the address. So with 6-bit address, you can address any of the byte which is present in the main memory. Now I'm saying that main memory is completely going to contain 64 bytes, right? And now assume that the page or the frame, each frame is going to be of 4 bytes. If each frame is 4 bytes, then number of frames will be equal to 64 bytes divided by 4 bytes, which is nothing but 16 frames are present in the main memory, right? So that means your main memory, I'm going to do it again, you might lose your patience, but then it is really important, please let me do it, right? Otherwise many people will not understand without this example. I know most of you know how to do it, but still, okay, if you know already this, please skip the video. I'm going to take a lot of time here, okay? So now 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16, right? See, I too don't like doing all this, but then if I don't, if I skip any part, assuming that you all know it, there might be someone who doesn't know it. That is why I'm doing it, okay? Please be with me, bear with me. Now this is frame number 0, frame number 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So totally 16 frames are there, right? And now assume that there is a process, there is some process, right? And the process size is what will be a good size? Let us say 16 bytes, right? And the page size is always equal to frame size, which is nothing but 4 bytes, right? And now the number of pages in the process, number of pages in the process is equal to how many number of pages will be there. If the process size is 16 bytes and each page is going to be 4 bytes, then how many pages will be there in the process? 4 pages, isn't it? 4 pages, which means now your process will contain 4 pages. Page number 0, page number 1, page number 2, page number 3. So remember this, I am always going to start my process, numbers here with 0 only. So 0 page, 0 frame and 0 byte, like that, right? I am not going to start it with 1, because in our binary numbers, if I start an address, it is going to start with all zeros. Therefore I am going to always start with zeros, okay? Now assume that this is page number 1, page number 0, page number 1, page number 2, page number 3, right? Then I'm saying that each page is going to contain 4 bytes. So just for the sake of concreteness, I'll even write the byte numbers, or I'll even show you what are the bytes which are present in each page. Now let us say the bytes present in this will be 0, 1, 2, 3, isn't it? And then 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, 15. This is how the bytes are present in the process, right? And now say this page number 0, right, is going to be loaded. Okay, watch it. Let us assume that I am going to load these pages, this entire process. This is process. This is the process which I want to load in the main memory, and this is the main memory, right? And say this is occupied, 0 is occupied, 1 is occupied, and we have got from frame number 2, 3, 4, 5 it is free. Then I'll try to assign, or I'll try to load this process into page numbers 2, 3, 4, 5, right? Therefore process P1 is present in pages, process P1, 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 right? Process P1 is present in frames 2, 3, 4, 5. Now what could be the byte numbers in the main memory of this process? Just see this. These two are occupied, and therefore I am loading process from here, right? And what will be the byte numbers here? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, don't worry, I am not going to write all the numbers. Okay. Now what happens is, once this process gets loaded in that main memory from frames 2, 3, 4, 5, now let us say this process is running on the CPU, and CPU now wants the byte number. Let us say it has generated the address 6, which means CPU wants this byte, right? So page number 1, byte number 6 it wants. Now if you watch it, if this process is loaded from page number 2, that frame number 2, then byte number 6 of page number 1 will be equal to 14th, right? So address 6 of the process is equal to 14th address in the main memory, right? You cannot directly go and give this address 6 to the main memory, because that will unnecessarily load a different address which is 6 here, which is not at all in your process, right? And that will be that will be error, isn't it? Therefore, even though CPU is generating a logical address of 6, which means it thinks that the process is loaded from 0 and it will ask for a word number, byte number 6, then you have to somehow convert it into number 14. That is all about the memory manager, right? Therefore, you should have a memory management unit in place in such a way that even though byte number 6 is asked, you should convert it into byte number 14. That is what you wanted. Now if this byte number 14 is presented to this main memory, that will fetch that location 14 and give it to the CPU, right? So that is what we want to do. That is all about the memory management unit. Then how are you going to do this memory management unit? What is the memory management unit in partitioning? We had two registers. One is base register, that relocation register, and other is a limit one, right? And similarly here also we want something that is called as page table. What is it? Page, PAGE, page table. And page table will look like this. For this process, how many pages are there? 4 pages, isn't it? So this is called page table. And one important thing to remember is, every process will have a page table, because every process will have pages and page numbers, and therefore every process will have a page table. You cannot have one single page table for all the processes. The reason is, every process will have page number 0, every process. Now when you have only one page table, how can you put many entries in the page 0? Therefore every process will have a page table, and that page table will contain information about where that particular page is present in the main memory frame, which means, watch it, see this. Now this page table will contain 0, 1, 2, 3, 4 entries. The reason is, we have 4 pages. Therefore, how many entries will be present in the page table? Always the number of entries in the page table will be equal to the number of pages in the process, right? So how many entries are there? 4 entries. Now each of these entries will contain where this particular page is inside the main memory. Now just see this. Where is page number 0 in the main memory? It is present in the frame number 2, isn't it? And where is page number 1 in the main memory? It is present in frame number 3. And what about page number 2? Present in frame number 4. And what about page number 3? Present in frame number 5. Therefore 0, 1, 2, 3 pages of the process are present in 2, 3, 4, 5 frames of the main memory. That is what is the relationship, right? Now by looking at the logical address, this is the logical address, right? So whatever CPU generates is called logical address, and whatever memory generates, memory management unit generates, and what has to be present to main memory is called physical address, right? Now using this page table, we are going to do this conversion. Fine. Now how can we convert it is, now watch it, 6. So first thing is, how many bits will be the logical address? So the number of bits that will be there in the logical address will depend on size of the process always, and the number of bits that will be there in the physical address will depend on the size of the memory, main memory, right? So what is the size of the process here? Size of the process 16 bits, 16 bytes. Therefore, how many bits are required? If it is byte addressable means we are trying to read every byte, or we are trying to address every byte. If it is byte addressable, and if there are 16 bytes, then 4 bits are required in the address, right? So because 2 power 4 is 16, isn't it? So 4 bits are present in the logical address, and what is the address generated? 6. So what is the value of 6? 0, 1, 1, 0, right? Now whenever this address is generated, then first you should think about what is the offset. Offset is nothing but size of the page. The size of the page is 4, right? So if the size of the page is 4 bytes, then how many bits are required to address each byte in a page? See, there are 4 bytes, and I want to address one of them. Are you understanding this? Each page contains 4 bytes, and now I want to find out 1 byte in the page. Therefore, how many bits are required? 2 bits, by 0001 1011. So with 2 bits, I'll be able to generate 4 patterns, and each pattern will be useful in identifying one of the parts in the main memory. I mean, one of the parts in the page, isn't it? Therefore, I can use 2 bits as the offset. And now if I use 2 bits as the offset, I can divide the logical address into 2 parts, right? So 2 bits, the least significant 2 bits will be acting as the offset, which will say what is the byte number, isn't it? The 2 bits are going to say what is the byte number, and then the remaining bits is going to say what is the page number, right? See, later I'll show you how to do this, but since it is a simple one, I'm just trying to do this easily, right? So now it means that the word number 6, the byte number 6 is actually present in page number 01. 01 means 1. So it is present in page number 1, and it is the word number byte number 2. 10 means 2, right? So these numbers are nothing but page number 1 and byte number 2, right? You please watch this example again and again, it will be simple to understand, right? So now what I mean to say is, whatever word you wanted, whatever byte you wanted, it is present in page number 1 of the process, and it is present at the second location inside that page, isn't it? See this? It is present at page number 1, and it is present at second location. This is 0th location. Second location means not second location, location number 2. Location number 0, location number 1, and location number 2. That is the meaning of this logical address. Now this one has to be converted to physical address. How can I convert it? Now I am going to go into the page table. I'll go to the page table into the page number 1, because it is showing that it is in page number 1, right? So when I go into the page number 1, it is going to say that it is present in frame number 3. Therefore, whatever you wanted is nothing but frame number 3. So I am going to convert it into physical address in such a way that I am going to take this frame number 3 and I am going to put it in the physical address, right? So the physical address should contain, one is frame number and other is frame offset, and frame offset should have only 2 bits. The reason is either the page size or the frame size, both are going to be same. Therefore the offset is going to be the same. So how much is this? 2 bits, and it is going to be 10 itself. Offset is going to be same thing, right? But then the number of bits required in this frame number depends on the number of frames there. How many frames are there? 16 frames are there, and in order to identify 16 frames, right, how many bits do you need? How many frames are there? 16 frames, and in order to identify 16 frames, how many bits do you need? 4 bits, isn't it? Therefore 4 bits are going to be the frame number, right? And now it is going to say that frame number is 3. Now how can you write frame number 3 here? 0 0 1 1, isn't it? So now this is the entire thing. This is the frame number 3, It is saying that frame number 3 and word number 2, right, or byte number 2, right, 0 1 2. Now if you watch this entire number, this number is 1110, right? So what is 1110? It is 14. So this number is nothing but 14, right? And now check that it is true. In the frame number 3, byte number 2 0 1 2 is nothing but 14. So that is how we could convert the logic. Let's say logical address. CPU assumes that the process is starting from point number 0, but which is not true. That is why they are all relocatable addresses and they have to be converted to physical addresses. Now how are you going to convert it? We need the memory management unit. Why can't we use the loader? Loader was doing this, right, relocation part. If you use the loader, you can only load it one time and you cannot take it out and again load it second time at a different location, isn't it? Because loader is going to replace all the relocatable addresses with absolute addresses, and once you replace it, you cannot move it around, and that is why we need a runtime machine or runtime binding or runtime relocation. So that runtime relocation is done by operating system. But then in operating system, if I use software, then for every instruction that is generated by CPU, we need to call the operating system. So instead of using that, I am going to use the hardware. So what is the hardware approach? I am going to use a table, right? So automatically whenever you run, you create any logical address, that address will be sent to the page table, and from the page table we get the frame number, and finally we get the physical address, and that will be sent to the main memory, and it will be faster. Got it? And one thing to remember here is every process will have its own page table. Therefore, if a process has to run, the process has to be in the memory as well as the page table also has to be in the memory. Now it is going to be complex, isn't it? Now before you access any word from the process, you have to go to the page table first, get the frame number, and then go to the memory. It is going to double the time because you have to access 2 times the main memory in order to get 1 byte. Okay, we shall look at that access time and all later, but first I think you understood how the translation is going to happen. See, paste this logical address. So if you understood this, I'll just try to show you here. Now logical address is whatever is generated by the CPU is called as logical address. Okay, I'll show it separately. I think you understood it, right? I'll show that separately, the remaining part. Fine.